So 5D, we're continuing to look at graphs and pictures and all that, but we're going to go a little bit deeper into it. Not deeper, but look at more complex graphs, as well as how sometimes they are misleading. So a few different more complex graphs is if we have a multiple bar graph where you have two or more sets of bars, so you can compare between two or more data sets. If the data categories are quantitative, then you can do multiple line chart. We actually saw that in 5C, that last example. Selling cars, that was actually a multiple line chart where you're comparing two different things at once. You can also have a stack plot where you stack data on top of one another. And so we'll look at examples of all of these. So first, let's look at a multiple bar graph, which is here. So what we have here is the median annual earnings of full-time workers by education attainment and gender. So here we have the salary down here, and we have the degree here, and then right next to each other in each category we have a value for men and we have a category for women. So as we look at this, we can compare, we look at a single thing as if it was a normal bar graph. We can look at all the men and compare men's salaries according to degree. So you can see that the higher the degree, the higher the salary in general. Same thing for women. So women also increase in salary as you increase in degree, but something special about the multiple bar graph is we can also compare men and women's salary with the same degree. So, like for example, for this professional degree, women's median salary is $80,000, but men's $119,000. So you can look at the difference with the same degree, the difference in the salaries between men and women. Okay, so here we have a multiple line chart. So here we're comparing years and the unemployment rate among different education levels. So this line on top is those who do not graduate high school, and this one is high school graduate, some college, and then a bachelor's degree or higher. So the different colors, of course, if you look at this on color online, it looks a little bit better. So for multiple line chart, again, you can look at each line individually, and you can see the trends. So we can see that for non-high school, it was almost at 12% in 1992, then it decreased a lot in 2000, and then increased a little bit, decreased again, it shot up really high in 2009. We're coming back down a little bit, back closer to 12,000 where we started in 2012. So you can see that trend individually. But you can also compare the different education levels at any period of time. So you can look at all the way across here. You can see that the non-high school graduates always have a higher unemployment rate as the next education level. So the more education you have, the less likely you are going to be unemployed, or the less amount of unemployment there is in that category. For each year. You can also compare like the differences. So like here, the differences between these education levels aren't as big, but there's a big difference between not graduating high school and graduating high school around the entire time. So that seems to be the biggest difference here. Okay, so that was what this question is here. Okay, example 2. This is a stack plot, stack bar graph anyway. So here, instead of having the side by side, they're going to be stacked on top of each other. So here, instead of looking at where it falls on this axis, we're actually going to be looking at the width of each piece. So here, this width is 3,131. This width here, from here to here, is 7,419. And you can get that by taking this amount here and subtracting this amount here. Right, so we want this width. So when you have things stacked up like this, you can compare a few different things. We can look at Um, we can compare the widths for different types of schools. So you can see that, let's see, that color here is tuition and fees. We can see tuition and fees, how that changes according to the type of school. We can also compare, each color individually and how it compares between schools. In this case, pretty much everything stays about the same except for this tuition. We can also compare the totals. So one good thing about having them stacked up is that we can look at each individual width, but we can also see the total for everything. So this total for everything for this public 2-year commuter is going to be $15,584. And we compare that to the totals for all 3 of these. So we can look at the individual widths, but we can also do the total without doing additional math there. So another thing kind of similar to what the widths are showing, we can see like the makeup of them. So we see that the private nonprofit 4-year on-campus universities are the most expensive. And so you can see what makes it more expensive. And in comparing each of these pieces, because we see that all 4 of these colors are about the same on all of these, we can see that just the tuition is pretty much the only difference between the cost of all 4 of these types of schools. Okay, similar to that one is a stacked line graph. Now this one's a little bit harder to read just because we don't have the nice even straight lines. But the same kind of thing though, when we're looking at each individual color, it is the width we're concerned about, not exactly where it lines up on this axis. We're more concerned about the width. So here we have 4 serious diseases in the trends in death rates between 1900 and 2011. So again, we can look at the width of all of them and compare it across time. So for example, pneumonia, which is this top one, it started out fairly, the largest was here at the beginning, but then as time goes on, it gets skinnier until it pretty much evens out for all this, but then it decreases even more. So pneumonia starts off with a bigger death rate, then as time went on, it's getting a smaller and smaller death rate, which is nice. Cardiovascular started out pretty large. This actually seems to be the largest of 1900. So the leading cause of death between these 4 would be cardiovascular. And then it gets bigger and bigger until it looks like it's largest, probably around right here. But then it starts to decrease again by 2010. Tuberculosis gets smaller and smaller until it looks like it disappears. Now, it doesn't actually disappear. People still catch and die from tuberculosis, so it's not 0. But it gets so skinny we can't actually display it on this graph because these are deaths per 100,000. So there's actually, there's going to be something there, but it's so small that you just can't see it next to this. Now, cancer of all of them is the only one that started off small and is getting bigger over time. So more people are dying from cancer now than there were in 1900, and it's been a steady increase. Okay, also on this, just like with the stacked bar graph, we can look at the total. So even though some of these are going up, some are going down, some are going up and down, we can look at the overall and see that overall the death rate is decreasing over time. So that's pretty nice. Okay. So besides bar graphs and line charts, we can just have pictures of different colors which show different information. Now this one looks a lot better in color, so I would suggest looking at it online if you haven't yet on your computer. I didn't have a color printer to print this out, so I'm stuck with black and white. Okay, so this graph shows the energy use per person by state. So for example, Wyoming, this one is actually the 7,000 to 79.99 range. And I think it's the only one that is that high. So this is between 7,000 and 8,000 gallons of oil per person. that's used in that state, and different states have different colors depending on how much they use. And this one, this is with contour map. So you can, this one is for temperature, but you often see these with like elevation, and that has the same kind of general rule. So what contour maps do is they have these borders that indicate you're crossing from like one level to another. So in this case, you're talking about temperatures. So each time you cross one of these lines, you are crossing this threshold. This, in this case, this 40-degree threshold. Either going from below to above or below to below, above to below, whichever direction you're going. With elevation, this would be a certain elevation, like 1,000 feet or something. So for example, if you're going from here to here, you're going from the 20s to the 30s, because we see 20 here, 30 here. So this is the 20 threshold, you keep going, and now you're at the 30 degree threshold. So from here to here, you're increasing temperature. From here to here, again, you're increasing because you're going from 30 to 40. And here you're in the 40s, here in the 50s, 60s, 70s. So each of these and each color, so all of this area here would roughly be the same degree. They're all here in the 30s. The closer the lines, the faster the temperature changes. So like if you're walking or driving from here to here, your temperature is going to change really quickly, as opposed to if you're going from here to here, right? So you're in the 30s and you get to the 40s, it's really not that big of a difference. But here, the same difference, the distance, you go from your 30s to the 60s. So the closer the lines, the faster it changes. So if you're looking at elevation, the faster you change elevation would be the steeper it is. Okay, so some questions about these. So we can use these together or we can use them separate. So for part A, what geographical characteristics are common to states with lowest energy usage per person? Okay, so it's harder to tell in here, but we can see that the lowest energy usage are going to be California, Nevada, Arizona, and then Florida and Hawaii. Those are the ones that have the lowest energy usage, and you can see from here, like, so if we're looking at California, Nevada, and Arizona, this area here, and then down in Florida, and then Hawaii, which isn't on this map, but they're all pretty much the warmer states. So here you're in the 60s and 50s, and here you're in the 70s and 80s, and Hawaii, of course, is always warm. So you can see that those states there are warmer states. So the warmer states seem to have the lower energy usage. But also, there are these up here that also have low energy usage. Now these aren't warm. These, on this date, are, I mean, some of them are in the 50s, but some of them are here in the 30s and 20s. So it's not the warm weather here, but those states up here, the New England states, those are all pretty densely populated. So warmer states and the more densely populated states have the lowest energy usage. Okay, part B, were there any temperatures above 80 in the United States on the date shown in figure 5.17? So we want above 80. So of all the thresholds, the only time we see 80 is here. So we'd have to cross the 80 threshold to get into the 80 degrees. And this is 70 to 80, so this area right here is the only part that went above 80 degrees. So this is yes in southern Florida. Now it doesn't show Hawaii, but Hawaii might also be pretty hot too, right? This is just the continental United States. Okay, another complex graph that we see sometimes are three-dimensional graphs. So these are most commonly seen like in software, where you can like move it around and you can see it in different perspectives, different viewpoints. But from here, we can now look at even more information than we can with just like the double bar graph. So here, we're comparing carbon dioxide emissions in different countries and in different years. So what we can see here is we can, if we want, we can compare each individual country over the years. So like for India, it started off small and they grow a little bit. China started off growing a little bit slowly and then it shot up real quick. The United States started off high and increased over time. We can also compare all the countries in a particular year. So we can say like in 2010 who had the most, and it looked like China did, and the US was right behind it. But Russia, Japan, and India were all fairly small, especially in comparison. We can also look at overall trends. So we can see that for most years, India was the smallest, and then Japan, then Russia, China, the US. But here, Russia was a little bit higher than China, and then here China surpassed US. So we can see the overall trends there as well. So we look at this question based on 518 above, about when did China surpass Russia in total carbon dioxide emissions? So China and Russia. So here Russia looks like it's more than China here. But we want to know when China surpassed Russia. So here Russia is still bigger, but here China is now over Russia, so that would be 1995. And then after that, China was always bigger than Russia. Russia is actually, I think, the only one that decreased here. Everybody else pretty much increased. Okay, so a few cautions when you're looking at graphics. Graphics are really easy to deceive. So we really have to kind of look at it closely. So one thing you have to pay attention to is percentage change graphs. Now we've talked about percentage change, and remember that percentage change is it depends on what you started with, right? So you start with something and then you either increase or decrease from that amount. So just roughly, let's say we're comparing tuition rates over time. So we have the different years, and this would be the percent change from your previous year. So this one, you may have a graph that looks like something like that. It could be kind of all over the place. So because it goes from like a higher percentage to a lower percentage, it seems almost like it's saying the tuition decreased there. But you have to be careful because this is percent change. So this could be like a 5% change, and this could be like a 4% change, but they're both a positive change, which means tuition is increasing this entire time. So your actual tuition over the years could be increasing. It may increase more between one year and the next, which is what the higher percentage is. But over time, it is always increasing because each of these percentage changes are positive. In order for it to decrease, you'd have to have a negative percentage change. Okay. Now pictographs. Pictographs are graphs embellished with additional artwork. There's an example in your book of a full page picture if you want to look at that one. The artwork may make the graph more appealing, but can also distract or mislead. And we'll look at an example here in just a minute. And there's perceptual distortion. Sometimes graphics are drawn in a way that distorts our perception. So let's look at this. The lengths of the dollar to the right represent the data, but your eyes tend to focus on the area. So here we're looking at the worth of a dollar. So if we say 1980, this dollar was worth $1. Okay. In 1990, that dollar was worth only 63 cents. Okay. So if we're comparing these, if you were to say, okay, how much of a difference was that? If you didn't have the amount here, and you had to guess how much did it decrease, well, in my mind, it looks like it would be like less than half, because if we look at this total area and this total area, it looks like it's a lot smaller, but it actually didn't. This is still more than half of that. So from $1 to 63. And then again, going from here to here, it looks again like it was like cut in half, but it's not. It's not quite that drastic. So if we were to compare just the lengths, so this length here, and this length here, and this length here. So going from this length, it's kind of estimated over here, it's really not as drastic as it looks. So this, you can kind of see that it's more like it's about 2/3 of the whole, and this again looks like it's more like 2/3. So area and distance are different, and sometimes our mind wants to interpret it one way when it's really not intended to be interpreted that way. Okay, another type of perceptual distortion is actually scale distortion. So sometimes the way they decide to show the scales is going to make the graph look either a lot better or a lot worse. So for vertical scales, let's look at women as a percentage of all college students. Now, if we look at this graph here, so between like 1910 to a little over 2000, it looks like the number of women in college is varying a lot, because it starts here, goes all the way down, and all the way up to the top of the graph. But if we look at the scale, this is only between 30 and 60%. So this is like a zoomed in part of the graph. Now, if we were to zoom out and we look at the total 0 to 100%, this is all possible, and then redo it, then we see that it's actually it stays fairly consistent here in the middle. We never have like a really small amount of women or a really large amount of women, but it does stay. That this says, it stays between 30 and 60%. But it doesn't change quite as drastically as this would make it appear to be. Okay, so that's vertical scales. Now we can also use horizontal scales. Now this one is an example of horizontal scales as well as perceptual distortion, because it adds all these pictures, which makes it look nicer, but it just kind of detracts from what we're really looking at. So here, normally in a graph, right, we have our horizontal axis is the one that's kind of a steady increase, and then the where it goes is going to change depending on where it's at. This one, it kind of makes it different. Our vertical is having the consistent change, this linear increase here, but our horizontal is all out of whack. So this makes it seem like the world is growing at a linear rate. So it took just as long to get to from 1 to 2 billion as it did to get from 5 to 6 billion, which is not the case. So if we look at the numbers here, our years, so it was 1 billion in 1804 and then 2 billion in 1927. Well, that was a difference of, what, 123 years? So it took us 123 years to get from 1 to 2 billion. Well, from 2 to 3, it only took 33 years. So visually, our mind wants to interpret it as if it took the same amount of time, but it didn't. It actually took like 4 times longer to get from 1 to 2 as it did from 2 to 3. And we can continue on from 3 to 4, it only took 14 years. So that was, it's a big difference. And we can keep going into the future. So we're not going to do too much of this in the homework, but you do need to be aware of this and know how to read some of these crazy graphs. And be aware when you see stuff like this in the news and in different studies that you really have to watch and see what it shows to make sure you're making the right interpretation of it. Okay, and that was 5D.